All right, chapter 7 here, our introduction to a hypothesis. So we have a question or something we're hypothesizing about, and we want to be able to test that to see how valid it is. So a quick example, you may have seen dogs that look like their owners, but is this just a coincidence, or do dogs really tend to resemble their owners? So there's a statistical question we can study that we can collect data on. So pictures were taken of 25 owners and their purebred dogs selected at random from dog parks. Study participants were shown a picture of an owner together with a picture of two dogs, the owner's dog and another random from the study, and asked to choose which dog most resembled their owner. Of the 25 owners, 16 were paired with the correct dog. Is this convincing evidence that the dogs tend to resemble their owners? Okay, to address this question, we want to come with this idea of if they did not resemble their owners at all, the participants' choices would be no better than a random guess for each pairing. And since there are two possible outcomes, we'd expect people to choose correctly about half the time. Of course, even random guessing, people will not always be correct half the time. Sometimes there'll be more, sometimes less. So while 16 out of 25 is more than 50% correct, how do we know if this is because dogs resemble their owners or it was just random chance that they did a little bit better than 50%? So we have three scenarios here. 25 out of 25 would be pretty convincing evidence. 10 out of 25 does not match that provided any evidence that dogs resemble their owners, since less than 50%, but is that convincing? And then 13 out of 25 is right around 50%, kind of 12, 13. So then which one then is convincing? Obviously A, maybe not B, and C is that middle ground. So our objectives that we're going to look through here is an introduction to hypothesis testing. The big ones are creating a null and alternative hypothesis, and then type 1 and type 2 errors. And later we'll get into tailed tests with the p-value, and then how to make those decisions, writing a claim from that. So a hypothesis test is a study of an important technique in inferential statistics. A hypothesis test is a process that uses sample statistics, which we've been working with, to test a claim about the value of a population parameter, right? And we've been working with that in chapter 6, samples to predict about a population. Now we're going to test that claim, take it one step further. Often seen in various fields such as medicine, psychology, business, rely on this hypothesis testing to make informed decisions. And as we've talked about, we can't test everything, and so we get samples, we collect the data on that, and then we try to use that to predict, and we can test it against hypothesis to make it even more reliable. Okay, so let's look at our example here. For instance, consider a manufacturer that advertises its new hybrid car that has a mean gas mileage of 50 miles per gallon. If you suspect that the mean mileage is not 50 miles per gallon, how could you show that the advertisement is false? So we can't test all the vehicles, but we can still make a reasonable decision about the mean gas mileage by taking a random sample and measuring the mileage of each. So for instance, to test that the mean gas mileage of all hybrid vehicles in this type is mu equals 50 miles per gallon. You take a random sample of n equals 30 vehicles and measure that the mileage of each. You obtain a sample mean, right? Our x bar is our sample mean there, and a standard deviation of s equals 5.5 miles per gallon. So does this indicate that the manufacturer's advertisement is false because we are less than that 50 miles per gallon? And so we're going to do something unusual here. We're going to assume the advertisement is correct. So we're going to assume that our mean of 50 is correct. Then you examine our sampling distribution of the sample means and taken from a population that had a mu of, or mean of 50 and a standard deviation of 5.5. So given from last chapter, the central limit theorem, you know the sampling distribution is normal with a mean of 50 and standard error of 0.5 over the square root of 30, which is roughly equivalent to 1. So we want to label below with both the x and z values for the previous hybrid vehicle problem. And then we're going to be a little more accurate here. So once we work this out, it's 1.004. And then we're going to label our graph here. So we know that z equals our x bar minus mu over standard deviation over the square root of n. So 47 minus 50 over our 1.004. So then z is roughly equivalent to negative 2.99. So we know negatives to the left, negative 2.99 is pretty far over here. Okay, and so labeling what we had, so our mean is 50. And the reason we know that is, remember back to last chapter, so the mean of our sample is equal to our mean of the population, which is 50 because of the central limit theorem, and then our standard deviation of x bar we found above, which was 1. So then as we build this out going each way, standard deviation, we can go down and up by 1 each. All right, so -1, -2, and then our -3. And then our -2.99 is right close to that -3. All right, so then we want to find what is the probability that the population mean is 47 or less than 47 miles per gallon. And so we're going to take that information over to Staplet. All right, we're going to look at our normal distribution. We have an x bar there. Not worry about the x-axis label. Our mean is 50. Our standard deviation was already set to 1, so we'll go ahead and plot our distribution so you can see it matches what we had. We want less than, so I'm going to be to the left of a value. And then my value we're looking for is 47, and we can go ahead and calculate that area. Right? We can even plot it there, and you can see where that's at. And rounded up, we get z is -3, right? And we are at z -2.99, so super close, and we get an area of 0.13. So if we take that back, we get an area percentage of 0.13%. So 3, based on that probability, is it likely that the population mean is 50 miles per gallon? And we would say no, because our probability is less than 5%. So what we would call this is an unusual event, and your assumption that the company's advertisement is correct has led you to an improbable result. A mean is not likely to happen. So either you have a very unusual sample or the advertisement probability is false. And logically, since we sampled well and it is unlikely to have an unusual, the logical conclusion is that advertisement probability is false. And this statement about the population parameter is called a statistical hypothesis. So when we write a statistical hypothesis, we carefully state a pair of hypotheses, one that represents the claim and the other its complement. And this is where we get our null hypothesis, denoted as H sub naught. And this hypothesis contains a statement of equality. It's either less than or equal to, or greater than or equal to. And then we have the alternative hypothesis, denoted as HA. And that's the complement of the null hypothesis. And is a statement that must be true if HO, or null hypothesis, is false. And it contains a statement of strict inequality. So HO is read as H sub 0 or H naught, and HA is read as H sub A. Okay, so a few examples of how this might be written. Right, so you can see our H naught is less than or equal to K, where our HA, our alternative, is strictly greater than K. And then you have the other three examples. Notice that our alternative hypothesis is always the exact opposite, or the complement of that. And then some important things here to help, right? Some key phrases and verbal statements of how to compare those. So our H naught statements, you can see all the different examples they have here compared to our alternative hypothesis statements and all the examples that they have there of how those might be written, right? We have the greater than or equal to, which could be at least or not less than. Right, and so those can be tricky, so this is a nice reference sheet for you to look back at. All right, so we're going to practice right now in stating the null and alternative hypothesis on a couple examples here. So we're going to write each claim as a mathematical sentence. We're going to state the null and alternative hypothesis and identify which represents the claim. So a school publicized that the proportion of its students who are involved in at least one extracurricular activity is 61%. So we always start with our HO, our null hypothesis. We state that our probability is equal to 0.61. We're going to write that percentage as a decimal. Our HA then is the complement of that, so then be not equal to that 0.61. And in this case, our claim is our null hypothesis, because they're saying that right there. Now, this one can be a little tricky because there's this at least one, but that's not the percentage that we're looking at. What we're looking at is this is 60, and is mathematically means equal. All right, go and try 5 on your own here briefly. All right, so we see here that we're looking at is less than 15, and so our HO, right, is now we're talking about a mean, not a proportion or probability. Hey, so 5, a car dealership announces that the mean time for an oil change is strictly less than 15. So strictly less than, remember, as a alternative hypothesis, and we're looking at a mean this time, so it's going to be mean less than 15. And then our null hypothesis is the opposite of that, so it's going to be greater than or equal to 15. And this, now, all alternative hypothesis is our claim, because that was the strictly less than 15 minutes. Again, remember, mean is our mu. That's why we use that. as opposed to in 4 where we had a proportion, so that was our P or our percentage on that. All right, let's look at 6 this time. So a company advertised that the mean, there's our mu again, life of its furnaces is more than 18 years. So HO, our null hypothesis, HA for our alternative hypothesis. And this time we're looking at more than 18 years. So this is a strictly more than 18, which means our null hypothesis is less than or equal to 18. And again, our claim this time is our alternative hypothesis because it was a strictly greater than value. All right, so now we know how to write our null and alternative hypothesis, identify which one's our claim based on how we read it. Is it a strictly less than or greater than or not equal to? Then it's alternative. If it is a null hypothesis, remember it's greater than or equal to, less than or equal to, or equal to. And then this brings us to the types of errors and our level of significance. So remember, no matter which hypothesis represents the claim, always begin hypothesis testing assuming that the equality condition in the null hypothesis is true. We always assume the null hypothesis is true. So then when we perform our hypothesis test, you make one of 2 decisions. We either will reject the null hypothesis, meaning that our alternative hypothesis is true, or we fail to reject the null hypothesis. All right, and this is huge here. We will never accept as true. We just fail to reject it. Okay, because our decision is based on a sample, there's a possibility that we make a wrong decision. And that brings us into our type of errors. There's 2 types, type 1 and type 2, appropriately named 2 types, 1, 2. So a type 1 error occurs if the null hypothesis is rejected when it is actually true. And what happens is it was actually true, but we rejected it as false by the testing that we got. Okay, so we ran our sample, we did our test, we rejected it based on what we got, but it was an error because the hypothesis was actually true. We call that a type 1 error. Now a type 2 error occurs when the null hypothesis is not rejected, when it is actually false. So this occurs when the null hypothesis is actually false, but again was not rejected by the testing. And so you can see here a nice little table of possible outcomes that organizes this idea for you. And so you can see the decision, there's 2. Do not reject or reject the null hypothesis. And then the actual truth of the null hypothesis is it's either true or it is false. And so twice you get correct decisions, and then twice you get reject decisions, or error decisions, I should say, not reject. Okay, and then there's a link there you can look at to review more hypotheses and errors as well in greater detail. All right, we'll continue diving into this on how we identify those better within our testing.